Take a look at electric dipole again. This is the second encounter to electric dipole. Again, I'll walk you through the definition, and this time, let us try to derive the electric potential of an electric dipole and somehow use that potential function to calculate the electric field intensity. The whole purpose is to justify, if you have a more complicated problem, trying to calculate the scalar potential and then perform the gradient is an easier approach as compared to calculating the direct vector electric field intensity. Okay. Again, if we have two charges with the same amount of charge but different in sign, and they are somehow separated by a distance d, that is an electric dipole. Di means you have two, okay? Dipole. This is the result that we derived on your slide number 15. Somehow using Coulomb's law and using approximation, where your observation point is very far away from the dipole, we have this result. So my main purpose now is to calculate the electric potential of the dipole, take its gradient, and show you can arrive at the same result. When we calculate the electric potential, remember, the potential is a scalar and is only 1 over r dependence. So everything is much more simplified. So the distance from the observation point to the positive charge is called r plus. The distance from the observation point to the negative charge is called r negative. So that's what I have 1 over r plus minus 1 over r minus. Here you have a minus sign because this charge is having a minus sign. Now, because we're still trying to assume our distance is very far away from the dipole, so basically r plus, this r plus, right? This r plus is r. R is my position relative to the origin in the spherical coordinate system. Okay? So r plus is r minus d divided by 2 cosine theta. R minus is r plus d divided by 2 cosine theta. So using that information, we can directly have the approximation of 1 over r plus and 1 over r minus. So these are just math, and you have the PowerPoint in front of you, so I can go faster. But just by doing that, okay, just by doing that, you quickly arrive at the potential as a function of distance due to the presence of these two charges forming an electric dipole. Super quick. Because you're dealing with scalar function, you don't really have to deal with the directions, the unit vectors. Okay? Okay? This is minor. I can just jump. So again, this is what we derived. Now we have the proper formulation to express the potential as the function of position. But in the end, we still want to know the E field intensity. Okay? So all we have to do is perform the gradient, and don't ever forget to take the negative sign. So this is the moment of truth. Have you understood gradient for all three different orthogonal systems? For spherical coordinate system, in the theta direction, you need to divide it by r. Okay? So why is gradient for this case only r dependent and theta dependent? You don't have the phi dependence. You don't have to perform the phi differentiation. Because in our current case, when we're far away from the dipole, we only have theta dependence and distance dependence. Everything is uniform, okay? Okay, so you can just have this result. Okay? So as I simplify, I have the E field intensity due to the dipole. It reads QD divided by 4 pi epsilon 0 r cubed, but now I have these two contributions. Okay? Now if you compare that to what we derived on slide 15, they should be identical, right? Aren't they? Aren't they supposed to be identical? But somehow, the result we got from Coulomb's law is having r dot d times r vector minus d vector. And we compare to the result we have now, derived from the potential first, and then making the negative gradient. They don't really look similar. So let's take one step further. Let's try to analyze it. This P, okay, we can always define the dipole moment itself being a vector. It's in the z direction because now we have the dipole aligned in the z direction. You have the charge and you have the distance. So basically, dipole moment is nothing more than the multiplication of the charge multiplied by the distance. And now you have a well-defined direction. Direction is defined as from the negative charge pointing towards the positive charge. So this is d vector. Okay? So Q times d vector is your dipole moment. This is your dipole moment. Z unit vector, how to change this Z unit vector into spherical coordinate system. That's what we covered in vector analysis, the first PowerPoint set for vector analysis. Z can be interchanged to R and theta. Right? So this is just a coordinate transformation. For the intention to cover the mathematical derivation, my intention is to show you the result of the electric dipole. Electric dipoles are so important to our understandings, to electromagnetics, right? So this is what we have from the textbook, figure 3-15. It's showing you when you have a positive charge and a negative charge with the same magnitude, but only difference in the sign, and they are somehow spatially distanced by d. This is all these circular structures in the solid lines are the electric potential being set up by these two charges. On the other hand, the dashed lines shows the resulting electric field intensity. So these are the E field lines. So try to compare, in your heads, or you can just draw it. Again, if we only have a single charge, how does the E field lines look like. When you only have a single charge, if you have a positive charge, all the field lines emit from the charge and going out, right? It's a radiant. And we also know that if we have a single negative charge, all the fields are terminated onto the charge, also in a radiant or sun-like fashion. But the importance of having the dipole is to bring these two charges together, right? So if you have this single charge, you know it's a radiant, sun-like field distribution for each one of them. But now you bring these two together. So when you bring these two together, for example, I have the negative charge here. So I'm going to use a different color. Okay? The white means originally for each single charge, you only have a single charge, you have a radiant pattern. But when you have the second charge having a negative sign but equal charge amount, you form an electric dipole. In this case, there's only one single E field line that remains unaltered, unchanged. That is this line. By definition, E field starts from the positive charge and ends up at the negative charge. So this is the only line that remains unchanged. For all the other lines, you have to have some kind of variation, right? Fields still emit from the positive charge and ends up at the negative charge, but they are somehow bended. All these other rays, they cannot be a single straight ray. They are all bended. I don't have a big board, okay? Okay, you have rays coming out extremely far away, right? So this is what this plot is showing you. Truthfully, right? After our analysis using Coulomb's law or using the electric potential and then you perform the gradient, doesn't matter. They all give you the same result. And through that, we understand, oh, all the field lines are now somehow distorted, right? When you have multiple charges, the field line distribution and therefore potential and electric field intensity are no longer that simple. They are no longer sun-like, but they are somehow, use your imagination. This is actually three-dimensional. So if you have a three-dimensional plot of the resulting E field lines, what does it look like? For Taiwanese students, we don't like to eat this type of food, but for Western friends, this is what you might eat every day, like a donut. We do have a Mr. Donut just across from our the main gate of our campus, right? So as I said, the entire thing is phi symmetric. So you can take this single cross section, you rotate around this z-axis, everything will be the same, and therefore you have this donut. So along it, you have the E field lines. You have donuts of various sizes. Okay? Oh, the way I'm plotting is somehow rotated 90 degrees. Okay. But take a close look and ask yourselves, do you understand what are being plotted for you? You have your voltage, right? So here, you have a closed solid trace, meaning above the positive charge, you have positive electric potential. V is also called voltage. So potential equals to voltage. So when you are above, you have positive potential. When you are below, you have negative potential. Why? In spherical coordinate system, cosine, right? When you are above, theta takes on the value between 0 and pi over 2. Right? Therefore, cosine is positive. So when you are above, cosine is positive. When you are below, your theta value is between pi over 2 to pi. You have negative sign. Right? So what happens when you are on the intersecting plane between the two charges? What I'm asking is, this is d over 2. This intersecting plane equally distanced between the two charges. What should the resulting voltage or potential be? To the left, you have positive potential. To the right, you have negative potential. So exactly on the bisecting plane, your potential needs to be 0. Cosine pi over 2, 0. Okay? So at this bisecting plane, you have potential 0. Above it, positive potential. Below it, negative potential. What other special aspect do you notice? Everywhere in this figure, the solid lines shows the equal potential contour. So try to link that to how I introduced gradient. This is like the height of the mountain, right? So gradually this is lower potential and we are walking towards higher potential. Everywhere the E field lines, the dashed lines, are perpendicular to the equal electric potential contour. Why? Come on, because it's by definition. Because E field intensity is defined as the gradient of V. Right? So everywhere, your E field line must be pointing perpendicular to your electric potential. But the direction has to be, the E fields has to point into the direction where you have potential reduction because you have a negative sign. Okay? So by looking at this plot, in the direction of E, you're losing electric potential. So basically, the outer lines, the outer solid lines shows you where you have the lower electric potential. So as you walk into the direction or against the direction of E field line, you gain potential. Right? So this is the importance of the dipole. We like to use the dipole to show you that when you have multiple charges, you are actually synthesizing more complicated E field distributions. But the dipole is a very good starting point to understand such synthesis, right? But once you master Gauss's law, Coulomb's law, there's no problem. You can just do the derivation. Okay? Point by point, we perform the integration. So I know I have the next slide for the students, but I prefer to wait. So I will introduce the electric dipole for the third time near the end of the semester. So I'm closing the first PowerPoint set here. I want to reserve the next slide for until the end, right? The reason is we have these two charges separated by D. But in this case, we're talking about a static case. So all you see is this beautiful graphs. But when you allow these two charges, the distance can be allowed to change as a function of time. Then you have a time-dependent electric dipole. Then you have the ability to generate waves. But I want to reserve that until the very end, when we talk about time variation of fields. So are there questions? Otherwise, I am going to close the first PowerPoint set. Static electric fields in free space. I am going to stop here. Any question from the students?